Hello, I'm Dharti Patel and today I will present about transient well testing in horizontal wells. A big thanks to our mentor Dr. Pawan Gupta for providing us an opportunity to present. Now let us start with the introduction. Transient pressure analysis of horizontal wells is more complex than that of vertical wells for the following reasons. First and most important being that the drilled horizontal wellbores are rarely horizontal, with many variations in a vertical plane along the well length, affecting pressure gauge inserted in the producing end of a horizontal well. Most horizontal well models assume that horizontal wells are perfectly horizontal and are parallel to the top and bottom boundaries of the reservoir. Calculation is not straightforward because horizontal wells exhibit negative skin factors. It is difficult to estimate exact production length of a long horizontal well. Productivity estimates in horizontal wells are subject to more uncertainty than comparable estimates in vertical wells. Further, it is much more difficult to interpret well test data because of 3D flow geometry. The radial symmetry usually present in a vertical well does not exist. Several flow regimes can potentially occur, and more significant and partial penetration and end effects commonly complicate the interpretation. In vertical wells, variables such as permeability, net vertical thickness, and skin are used. Horizontal wells need more detail. Not only is vertical thickness important, but horizontal dimensions of the reservoir relative to the horizontal wellbore need to be known. Steps for evaluating horizontal well test data. There are three basic steps involved in evaluating pressure transient data from a horizontal well. First, identify the flow regions. Evaluation of data from a vertical wellbore will generally center on a single flow region, such as infinite acting radial flow, known as the middle time region. However, a pressure transient test in a horizontal well can involve as many as five major distinct regions that need to be identified. These regions may or may not occur in a given test and may or may not be obscured by wellbore storage effects. Second, apply the proper procedures. Each flow region can be modeled by an equation that can be used to estimate important reservoir properties. At best, only groups of analytical parameters can be determined directly from equations. It is imperative that the proper analytical and graphical procedures be applied to the data. In many cases, when solving for specific parameters, the application of these analytical expressions may involve a complex iterative procedure. Third, evaluate uniqueness and sensitivity. Experience indicates that the results of horizontal well test analysis are seldom unique, so it is important that uniqueness and sensitivity of the results to the assumed properties be evaluated. Simulation of the test using properties that have been determined from the test can confirm that at least the analysis is consistent with the test data. A simulator can also determine whether other sets of formation properties will also lead to a fit of the data. Horizontal well flow regimes. Different formation properties can be calculated from the data in each of the five different flow regimes. Any flow regime may be absent from a plot of test data because of geometry, wellbore storage, or other factors. Nor does the fact that they can appear mean that they do appear. The five different flow regimes that can occur are early-radial, hemi-radial, early linear, late pseudo-radial, and late linear. Figure 1 shows a horizontal well with length Lw within a reservoir that is assumed to be a rectangular parallel pipe or a box reservoir drainage area. In this discussion, it is assumed that the axis of the coordinate system coincide with the direction of principal permeability and the well produces over its entire length Lw. The axes of this box are usual x, y, and z axis. Notice that the x-axis is measured along the bottom edge of the reservoir, going from left to the right in the direction perpendicular to the well. The y-axis lies along the axis from front to back of the reservoir parallel to the wellbore. Z-axis is oriented in the direction of reservoir thickness. The total width of the reservoir perpendicular to the wellbore is AH, and the total length in the direction parallel to the wellbore is BH. The total height of the reservoir is net pay thickness H. Notice the parameters for distance from the well to the various borders. Along the axis of the well, the shortest distance from the end of the wellbore to a boundary is small dy, and the longest distance from the other end of the well to the boundary is capital Dy. In the vertical direction, the shortest distance to a vertical boundary is small dz, and the longest distance to a vertical boundary is capital Dz. Characteristics of flow regimes. Now, let us discuss all the flow regimes one by one. Early-radial flow. Consider a well producing at a constant rate. The early-radial flow regime occurs before the drain pressure transient caused by production encounters the either vertical boundaries in the reservoir. Figure 2 shows a radial flow pattern penetrating out into the reservoir. Actually, however, this flow pattern is likely to be elliptical, moving further into the reservoir at a given time in high permeability X direction than in the low permeability Z direction. This phenomena causes no significant complications in our analysis. Hemiradial flow, when the wellbore is much nearer one vertical boundary than the other. Another flow region called half-radial or hemiradial flow may exist as shown in figure 3. Hemiradial flow can occur immediately following the early radial flow region if the well is much nearer one vertical boundaries than the other. Eventually, the area affected by the production will include the entire thickness of the reservoir. When that happens, a linear flow pattern may develop. Ultimately, after a time period, the flow will begin to come into the wellbore from beyond the ends of the well. Until these end effects become more important, early linear flow continues. Once end effects become more important, a transition period is followed by a late pseudo-radial flow region. This flow region continues until the area affected by the production reaches one of the sides of the reservoir. Once the area affected is the entire width of the reservoir, that is, the pressure transient has reached both sides of the reservoir, then the late linear flow region begins. Now, let us see how we can identify the different flow regions in the wells. All these flow regions in a test can be identified on a diagnostic log-log plot of pressure change delta P and pressure derivative P dash against logarithm of time, as shown in figure 7. The delta P curve is represented by a bold continuous line and P dash curve is represented by dotted line. A unit slope line appears during wellbore storage, a horizontal derivative during early radial flow, and then later in pseudo-radial flow. A half slope line in early linear flow and then in late linear flow. These half slope lines appear on the derivative but not on the pressure change curves. This does not imply that all these flow regions will appear in a given test. In fact, that would be rare, but these are shapes that identify flow regions that may appear in the test being analyzed. We will now discuss the equations governing early radial flow. Early radial flow is similar to the radial flow period in a vertical well. The governing equation for this flow region is given by equation 1. Data for this period may be masked by wellbore storage effects, but when present, they may be analyzed on a semi-log plot. The early radial flow region may, in theory, start at time 0 in absence of wellbore storage effects. The end of early radial flow region may occur when the transient reaches a vertical boundary or when flow comes from beyond the end of the wellbore. The end of this period is smaller of these two values. Equation 2 says that the period must end when the transient reaches the nearest boundary, small dz, from the well. This equation includes permeability in vertical direction. The radial flow regime may also end when flow from beyond the end of the wellbore becomes important. This is given by equation 3, where Lw is the completed length of the well and Ky is the permeability in direction parallel to the wellbore. The actual end of is lesser of the two times calculated from equations 2 and 3. It is helpful to check the expected duration of the early radial flow region after estimating the parameters necessary to make these calculations. Equation 1 suggests that possible radial flow on the diagnostic plot be identified and then bottom hole flowing pressure be plotted against time during the appropriate time range on a semilog coordinates. The slope of the straight line that results is given by equation 4. The group root kx kz can be found from the slope MERF by equation 5. Effective completed length of the well must be known to make this calculation. This is not necessarily the same as the perforated or completed length of the well. Some sections of the well may not produce at all. The equation for calculating the altered permeability skin SD for radial flow is given by equation 6. When analyzing a build-up test rather than a constant rate flow test, plot the Horner time ratio or equivalent time on horizontal axis of the semilog plot and then plot shut-in or equivalent time on the vertical axis. Note that this plotting is correct only if Tp plus delta T and delta T appear in the same time period simultaneously. That is, radial flow must exist at both time Tp plus delta T and time delta T. This is unlikely because radial flow regime may exist at time delta T, but a different flow regime is likely at time Tp plus delta T. Hemiradial flow. The hemiradial flow period will occur only when the well is close to one of the vertical boundaries, either the upper or the lower, and is analogous to a vertical well near a fault. The governing equation is equation 1. The horizontal derivative on the diagnostic plot identifies hemiradial flow. If data appear to fall into this flow region, a straight line on a semilog plot would provide more confidence that radial flow has been identified. Consistency checks in the analysis coupled with a well survey will be required to distinguish hemiradial flow from early radial flow. The time range in which the analysis for hemiradial flow is valid begins after the closest vertical boundary small dz affects the data and before the farthest boundary capital DZ affects them. In the absence of wellbore storage, the start of hemiradial flow is given by equation 2. Note that the start of hemiradial flow regime involves the shortest distance to a vertical boundary and permeability in vertical direction. However, wellbore storage will most likely determine the actual start of hemiradial flow. The end of hemiradial flow occurs when pressure is affected by farther vertical boundary or flow from beyond the ends of the wellbore, whichever occurs first. It is the smaller of the times calculated from equations 3 and 4. If the hemiradial flow regime ends when pressure reaches the farthest vertical boundary, it depends on distance capital DZ and vertical permeability Kz and is given by equation 3. When the appearance of the end effects, that is, flow from beyond the ends of the wellbore, causes the end of the hemiradial flow regime to appear. The end of the flow regime occurs when TEHRF equals to 125 LW square 5 mu CT upon KY, which is equation 4. The completed length of the well LW and the permeability KY appear in this equation. These parameters determine when enough flow has come from beyond the ends of the wellbore to distort the radial flow pattern that appeared earlier. Equation 5 gives the slope of the semilog straight line for hemiradial flow, MHRF. The multiplier 325.2 is twice the multiplier for early radial flow. The equation to estimate the damage skin factor is also similar to that for radial flow but has a multiplier that differs by a factor of 2. The equations relating slope and permeability and equation for skin are similar in build-up test to those for a drawdown test. The pressure change in the equation for skin P 1 hour minus PWF. The semilog plots of build-up test data from Hemiradial flow region cannot be analyzed rigorously using data from Horner plot unless the pressure data at Tp plus delta T and time delta T are simultaneously in this flow region. As a practical matter, the Hemiradial flow region is likely to appear clearly in the build-up test only when the producing time is much greater than that of the shuttle. Early linear flow. The governing equation for early linear flow is given by equation 1. The convergence skin SC is discussed in the next slide. The start of early linear flow region depends on the farthest distance to a vertical boundary, capital DZ, and vertical permeability Kz as given by equation 2. Not until flow reaches that farthest vertical boundary can a linear flow pattern begin toward the well. This flow period ends when fluid flow from beyond the ends of the wellbore, thus given by equation 3. Notice that the end depends on effective completed length of the well Lw and on permeability in direction parallel to the well Ky. This is the time in which end effects, that is flow beyond the ends of the well, begin to significantly distort the linear flow pattern. The early linear flow region is identified in a drawdown test with a half slope of the derivative. Because of the skin effect, the pressure change curve on the diagnostic plot will only approach a half slope asymptotically. For data identified as being in this flow region, plot pressure against square root of time. The slope of straight line on such a plot, MELF, can be used to estimate the square root of Kx, the horizontal permeability perpendicular to the well, that is given by equation 4. To calculate the damaged skin, we can use equation 5. This equation includes a convergence skin, SC, which is given by equation 6. This convergence skin is an additional pressure drop that acts like a skin effect caused by flow moving from throughout the entire length of the formation until it converges down to the small wellbore in the middle of the formation. This convergent skin is defined in the terms of ratio of permeability in the x direction, which is perpendicular to the wellbore, to the vertical permeability. It also involves the distance to the nearest vertical boundary, small dz, and the net pay thickness, h. Late pseudo-radial flow. The governing equation for late pseudo-radial flow is given by equation 1. The late pseudo-radial flow period occurs only if Lw by Bh is less than 0.45. Here, Bh is the dimension of the reservoir parallel to the wellbore. As long as the completed length of the well is relatively short compared with the length of the drainage area, late pseudo-radial flow can occur. The start of this flow period occurs when fluid flows from the well beyond the ends of the wellbore. It is approximated with equation 3. This starting time depends on the completed length of the well Lw and on permeability in the direction of the well Ky. The end of this period, like others in this section, is approximated by minimum of results of two calculations. First, given by equation 4, depends on dy, the length of the wellbore, Lw, along with Ky, the permeability in the direction parallel to the wellbore. This is the time at which horizontal boundary effects first appear. The other equation gives a time at which radial flow pattern begins to be distorted depending on the shortest distance dx from the well to a boundary perpendicular and to the wellbore and on Kx, the permeability in that direction, which is given by equation 5. Whenever boundary effects first appear, whether in a direction that is parallel to the well or perpendicular to the axis of the well, the late pseudo-radial flow period will end. The diagnostic plot helps identify the late pseudo-radial flow regime with the characteristic horizontal derivative. For data in the appropriate time range, prepare a semilog plot of pressure against time for a drawdown test. The slope of this plot will be MPRF, and the relationship between that slope and the square root of Kx, Ky, or permeabilities in the horizontal plane is given by equation 6. The skin equation is similar in form to that seen before, which is given by equation 7. Again, the total skin depends on delta P 1 hour. The convergence skin is subtracted from total skin to determine the damaged skin. For a build-up test proceeded by a production at a single rate, plot pressure against Horner time ratio on a semilog graph. Permeability is calculated from equation 6, the same as for drawdown test. The skin equation is basically the same as for drawdown test, except that the delta P1 hour is now P1 hour minus PWF. To obtain P star, the extrapolated pressure, extrapolate the semilog straight line to a Horner time ratio of unity. Semilog plots of build-up test data from the late pseudo-radial flow regime cannot be analyzed rigorously using Horner plot unless pressures at Tb plus delta T and at time delta T are simultaneously in the pseudo-radial flow regime, which is highly unlikely. However, little error appears if the producing time before shut-in is much greater than the maximum shut-in time achieved in the build-up test. Late linear flow. The governing equation for late linear flow is given by equation 1. The late linear flow regime starts after the pressure transient has reached the boundaries in the z and y directions, and the flow behavior with regard to these directions has become pseudo-steady state. The start of this time period is the maximum of the two equations. The first depends on the time to reach the boundary, capital dy, beyond the end of the horizontal well. It also depends on the permeability Ky in the direction parallel to the wellbore, which is given by equation 2. Another requirement for the start of the late linear flow regime is the time to reach the maximum vertical distance, capital Dz, divided by the vertical permeability Kz, and is given by equation 3. Usually, the start of the late linear flow regime is dictated by the time to reach the boundaries in the y direction. The end of this period is given by equation 4. The end of the late linear flow regime depends on reaching the nearest boundary in the direction perpendicular to the wellbore, which is the distance small dx, and on the permeability kx in that direction. Identify the late linear flow regime by half slope on the derivative in the diagnostic plot of drawdown test data. The pressure change may approach a half slope asymptotically. For data that appear to be in this flow regime, plot pressure against the square root of time from the slope MLLF of the plot. Estimate permeability in x direction from equation 5. Alternatively, if Kx is known from an early linear flow regime, estimate Bh, the length of the drainage area, from equation 6. This late linear flow regime is the only period that provides the data to calculate the total skin S, including the partial penetration skin SP and the convergence skin SC. To calculate the damaged skin SD, use equation 7. The total skin depends on delta P at T equals to 0. Subtracting the partial penetration skin SP and the convergence skin SC from the total skin yields the damaged skin. The partial penetration skin is a complex function that is calculated using correlations. For a build-up test, plot pressure against Horner time ratio from the slope MLLF, calculate Kx with equation 5. Exactly the same as for drawdown tests. Or if Kx is known, estimate the length of the BH of the drainage area using equation 6. Calculate the damaged skin SD from a pressure buildup test from equation 7, where delta P at t equals to 0 equals to P at t equals to 0, which is extrapolated from the graph, and PWF minus PWF. Note that the same difficulty arises using superposition to find plotting functions. Plots of build-up data from the late linear flow regimes as existed with the previous flow regimes. Pressure at both time Tp plus delta T and time delta T must be in the late linear flow regime for a tandem root plot to be valid. However, if delta Tp is very high than delta T max, there is little error. Running horizontal well tests. The measurements in horizontal wells are usually made above the wellbore with the pressure gauge still in the vertical section. The test string may often be too rigid to pass through the wellbore. However, in most cases, conventional hardware can be used for horizontal well tests. With longer horizontal wellbore storage is an inherent problem for testing, even for build-up tests with downhole shut-in. As mentioned previously, problems arise in conducting build-up tests with short duration production periods because superposition is inappropriate. Therefore, Horner plots and tandem root plots, which depend on superposition being applicable, are often inappropriate. Another problem in conducting build-up tests following a short production period is that significant pressure gradients along the length of the wellbore may cause cross-flow within the wellbore during shut-in. So, fluid may flow from one region to another in the wellbore. These gradients can be removed and this cross flow eliminated by a longer duration flow period preceding a build-up test. Thank you for watching this video. In case of any doubts, please comment below.